Hello, everybody. It is Mr. Winchell again, here with you talking about the last part of our units in exponents. We are going to be looking at how to graph exponential functions in this video. And I'm actually going to be splitting up these notes into two videos because it's going to take a little bit of time and I don't want to overwhelm you too much. So in this video, we are going to go over how to graph exponential functions and what the graphs look like and how to plot those points. So with that being said, let's get started right away. To begin this lesson, I'm going to give you just a little bit of an intro as to what exponential equations look like. So here we have y equals a times the quantity b raised to the x power. Now, an example of something that is in this form could be y equals 3 to the x power. Now that looks a whole lot simpler than y equals a times b raised to the x power. But just note that this is going to be the same as y equals 1 times 3 raised to the x power. The a value is typically 1 if you do not see a value outside of parentheses. So we don't really need to write it, but it does get a little bit more important when you do exponential equations involving growth or decay and like word problems. But for now, we're just going to look at that number that's inside the parentheses or attached to the exponent as your base. So just to clarify, when we're looking at exponential equations, the variable must required be in the exponent to be considered exponential. Just because you have something that has an exponent doesn't mean it's necessarily an exponential equation. So we classify these equations as growth or decay. So if the number inside the parentheses or the number attached to your variable in the exponent is greater than 1, then it represents growth. So for instance here, my example of y equals 3 raised to the x, that would be exponential growth. I know this because 3 is greater than 1. And on the flip side, if that number is less than 1, it will be exponential decay. An example of this could be like y equals, and you'll usually see parentheses, 1/2 raised to the x. This, of course, is decay because I know that 1/2 is less than 1. However, you can sometimes see equations that have fractions. So you might say to yourself, oh, well, that number is a fraction, so it's got to be less than 1. But just be careful that that is actually growth. So this is how I classify my exponential equations. One of our learning goals is if you look at an equation, can you recognize if it's exponential? Can you recognize if it's growth? Can you recognize if it's decay? Or neither. So to conclude this slide, we have these 4 examples down here. Now remember, all I'm looking at is the base. I care not for the number on the outside, that a term or the coefficient. If 2 is greater than 1, then my exponential equation is showing growth. It's that simple. A lot of students get mixed up with the number on the outside of the parentheses, but all that I'm looking at is this number. Now, sometimes it can be a fraction, sometimes it can be a decimal, sometimes it can be an expression like 1 plus 0.09. Well, you can simplify this to 1.09, and that, of course, is greater than 1. So that is going to be exponential growth. And then, like I had mentioned before, just because an equation has an exponent doesn't necessarily make it an exponential equation. Y equals x squared has an exponent, but the variable is not the exponent. So this is not exponential growth, nor is it exponential decay. If you actually want a little look into your future, that is a quadratic equation, and we deal with that in Unit 8. So now that you can recognize exponential equations and differentiate between exponential growth and exponential decay, let's look at what the graphs represent visually. So here we have our first example of trying to graph an exponential growth equation. On the right, you can see f of x equals 3 to the x. Let's just remember that f of x and y are interchangeable. So this could say y equals 3 raised to the x power. So the way that we are going to deal with this in our algebra class is we're going to create a table of values. We typically like to use 5 values, and that's going to go from -2 to +2. And we're going to fill out this table of values. Remember, each of these tables of values are going to create, ordered pairs that we'll plot, and then we'll try and see what kind of shape that this function creates. So to demonstrate your ability to understand these equations, you're going to show work for at least 2 of the values. Now, for the sake of showing examples that will be meaningful, I'm going to show you -1 and +2. I like to include a negative and I like to include a positive just to show you how the operations work and what we're expecting in terms of your work. So here I go. So I'm going to plug in -1 in for x. So you'll have to know your exponent rules for this to make sense. F of -1 is going to be equal to 3 to the negative first power, while the negative exponent rule tells me that if I have something that has a negative exponent, then it must flip from the numerator to the denominator, and it must switch its sign. So this means that I will have a 1 over 3 to the first, and I don't need to put the to the first. 1/3 is going to be my final answer. So when I come over here, if I plugged in -1, I got out 1/3. And yes, you are going to use fractions. In fact, we really encourage you to use fractions. And we'll get to plotting that point, but I just wanted to show you how to calculate what the input of -1 would give you for y equals 3 to the x. So now a little simpler, I would say. I'm going to just show what I would get if I plugged in 2. So this, if you remember from back in the day, is just function notation. So I just plug in 2 into f of x's rule. 3 squared just turns into 9. So then I have my second value, which is just here. Now, remember, I just have to show work for at least 2 of these values, but I am, just for the sake of this video, going to also show you what this would look like in terms of all the other values. So 3 to the first is just 3. Now, this is great. Honestly, this is like the freebie. Any number except 0 raised to the 0 power is just 1, so you're welcome for that. And now, this is where trying to establish patterns might come in handy. So 9 can be rewritten as 9 over 1. 3 can be rewritten as 3 over 1. And then 1 can be written as 1. But you're going to notice something about -1 and +1 in this table. You might notice that the fractions are simply just flipped over because 1 over 3 is the same as 3 to the negative first power. And that is very similar to 3 over 1. So the reason why I'm saying this is because if we can generate, not 2. If we can generate one of these values, then we can kind of find its flipped case. For instance, 3 to the negative second is going to be 3 squared flipped over. So I don't even have to do the math to get this value. This is going to be 1/9. Okay. That can be extremely useful in terms of trying to save you work and time, but I did want to just show you where all of those points are coming from. So now let's go ahead and plot these points. I'll start with 0. 0, 1 is where my function is going to start. That's my y-intercept, if you want to think about it that way. Then I have 1, 3. And 2, 9. So interestingly enough, in this table, you're going to notice that these points are not the same distance apart. In fact, right now, I couldn't even connect them with a line. And that's a good thing because this is non-linear. This is an exponential curve. But now it gets a little trickier when it comes to the fractions, because 1/3, like -1 comma 1/3, I'm just really gonna just estimate this point to be about a third up in that box. And then -2 comma 1/9. Now I'm getting even closer down to the bottom of that x-axis, but not quite. So my goal now is to try and connect all of these points with an exponential curve. All right. It's just, once again, important that you remember that this is not a line. This is not linear. So I am going to start my tail on the left side of the graph and then kind of scoop up. Ooh, I kind of missed there. So I'm going to actually just redo that. The curse of being a lefty. Shout out, 10% of the population. There we go. Now, please note that I am going to put arrows, and I have plotted my exponential growth. Now, whenever I look at these graphs, the first thing that comes to mind is that escalated quickly, and that's exactly what you should be looking at here. This graph is exponentially increasing. So it's not some constant rate of change. It's tripling every value of x. So like the next table value would be like 3 comma 27, 4 comma 81. Like it's increasing more and more and more and more as you go. So this is how I plot the graph of an exponential growth function. Let's now look at exponential decay. All right, so we have the function f of x equals the quantity 1/2 raised to the x power. Now this is just like a notation thing, but I am just going to show you that this is, you're really gonna see this written as y equals like a fraction, 1/2 raised to the x. Also, I know that this is decay because my base 1/2 is less than 1. So I know kind of in my mind what this graph is gonna look like, but this notes video is going to just try and show you where those values are really coming from. First off, I just want to just say that I have one of these table values right away. 0 exponent rule states that anything except 0 raised to the 0 power is 1. So I don't really have to do much because 1/2 raised to the 0 power is just 1. But I do want to demonstrate once again, showing you the work for -1 and +2. Your work does need to include at least 2 examples, so I'll show these 2, and then we'll fill out the rest of the table. So starting with the -1, this one's going to be tricky. Whoops. Oh, okay. So I guess that's how I zoom out. So the negative exponent rule states that we need to distribute this negative, like with the power rule, is one of my first steps. Or you could just think about like flip the fraction. So I'll say, of course. So I'll say 1 to the -1st over 2 to the -1st. And because both of those exponents are negative, I'm going to flip-flop these numerators and denominator, and I will get 2. I can even say 2 over 1, and I actually will. So when I plug in -1, I get out 2, or I'll put over here 2 over 1. Okay, so that was the example of using -1. You're going to notice that I simply just kind of flipped 1/2 over as a fraction. Now, when I go to use +2, I'm once again going to use the power rule to distribute that exponent of 2 to both the numerator and the denominator. So we'll get 1 squared over 2 squared, and 1 squared is just 1. But 2 squared is 4, which means when I plugged in 2 for x, I got an output of 1/4. Okay? So you're going to notice that when I'm looking at this table of values from 2, 1 to 1/4, these values are decreasing as my x's are increasing. This is what makes it exponential decay. All right, I will just now go back to my previous slide, and I will have you notice that as I look at these values of y are increasing because this is exponential growth. So this is one of the differences between exponential growth and exponential decay. But I'm going to go ahead and fill out the rest of these table values. So 1/2 raised to the first power, any number raised to the first power is just itself. So that's just 1/2. And now does the table of values trick work for negatives? So you're going to notice that 1/2 and 2/1 are in fact just fractions that are flipped. It's 1/2 for +1 and 2/1 for -1. So if I know that +2 is 1/4, guess what? I now know that this value down here is 4, or 4/1, because I just flip its value from its positive counterpart. So once again, this table of values is decreasing y's as the x's are increasing. So I'm just going to go ahead and plot these out, and so you can actually see what this function looks like. I'll start with -2, 4 on my graph over here. So here we go. Nice. Remember, it is an exponential curve. So -1, 2, 0, 1. 1, 1/2. Once again, fractions are okay. In fact, they are encouraged, because as you can see in this graph, it appears as though the distance between these points is getting cut in half each time. Like if you actually notice, 4 goes to 2, that's -2. 2 goes to 1, that's -1, or half of the distance. So this is going to kind of look a little bit like, I'm going to try and be as accurate as I can, like this. Now, this forms an exponential curve that gets closer and closer and closer to the x-axis, but it doesn't quite hit the x-axis. Because if I'm cutting something in half, over and over and over again, then it will never get to 0. And that's a really important point of these things that we get in exponential curves called asymptotes. Okay, you'll notice that the tail here of my decay is on the right side of the y-axis, but when I look at growth, the tail is on the left side. But this tail here is actually a little border. It's a limit where that function's never going to actually equal 0. Because if I keep slicing these things by 3s, if I'm going backwards in this table, it'll never get to 0. Because if I divide two numbers, it's never going to equal 0. So this is just known as exponential decay. And this little point here, the x-axis, I guess I will label it, is called an asymptote. Okay, so that is going to conclude video part 1 of these notes. In this video, you were able to try and distinguish if an equation is exponential growth, decay, or neither. And you saw the process for graphing exponential growth and exponential decay. Please note that you are going to have to show work for calculating these values in your assignments, so please be mindful of that. But thank you guys for joining me in this video. I hope you found it useful. If you have any questions, just ask your teacher. I'm sure they will definitely clarify the information. So once again, my name is Mr. Winchell. I hope you found this video useful. Tune in for part 2 on my YouTube channel. Like and subscribe, and I'll talk to you guys later. Thanks.